Hello, Charlie B here. Welcome to part 3 of cryptocurrency from scratch. In this part we are going to be signing and verifying the transactions that we created. If you recall from the previous 2 sessions, we have down here the transactions with a consistent amount of money, tokens, changing hands through the transactions. And then the previous session was creating some cryptographic primitives that we're going to use. Here is we created a private key. We're able to turn that private key into text. That private key has a corresponding public key, which we can also turn into text. And then we can turn the public key back from text into an actual public key. And then recall that in Bitcoin, an address is a hash of the public key. So we have that address primitive. And then we can sign and verify, so signing with the private key, verifying with the public key, a particular message. And we're going to use those to verify that our transactions down here are not only numerically consistent, but also that only the owner of an address is able to spend the outputs from a transaction. So, what does it mean to own an address? What that means is twofold. The first part is that, like I said, the address is a hash of the public key. So you have to, as the owner of the private and public keys, you have to show that your public key does indeed hash to the address. And then you have to sign the transaction with your private key to verify that the owner of that public key, and thus the owner of the address, consents to move the tokens in that unspent transaction output that's sitting at that particular address. So, how are we going to do this programmatically? So the first thing that I want to do, actually, somebody pointed out in the comments that there is a rather nasty bug in this verified chain part because, let's see, there is no verification of negative spends. So I could have a transaction with 0 input, and I could send minus 1,000 coins to one address and plus 1,000 coins to another address. I would never spend the minus 1,000 coins, but then I could spend 1,000 coins. So I have to verify that all of the output amounts are greater than 0. Yes. They can be 0. Yeah, greater than or equal to 0. So let's figure out where we're going to put this. Check. So here we go. Input amounts. And for the outputs here. So I'm going to have to add another loop. Bummer. Okay. For out in tx output. There we go. Outputs. Out amount is less than 0. We're going to return false right there. That should check. That should stop anybody from spending negative coins and getting a payout as a result. So with that bug fixed, let's return to our transaction. So when we're making a new transaction, we are going to also supply the public keys. And those public keys are going to correspond to the input addresses, one for one. Let's add that down here. Keys. There's that. Outputs remain the same. And yep, this is all the same. So that's pretty straightforward in terms of creation. So let's, first of all, let's bring this back. This guy can go back to being named. Let's just check that I didn't screw that up. I did screw that up. Oh yeah, okay. Okay, so I added an argument and then didn't add it to any of the code down here. So it's a slight oversight on my part. So when we make a transaction, we need inputs. We need the ID. We need the inputs. We need public keys, which, since we're not actually doing anything with them yet, doesn't really matter. Just add it to make Python happy. I'm also going to reformat this in a sec. Just want to check that I didn't screw anything up. Okay, good. And then, since we did do this, let's say, so we have 100 input into this transaction. So let's do minus 100. And we're going to take 100 coins in. We're going to add minus 100 coins and then take out 200 coins. False. Fantastic. Okay, now back to the important business. Not that that's not important, but the important business of signing. Okay, so this remains the same because this is the Coinbase so-called transaction. This, well, we need some keys, right, to start with. Let's create 3. B, C. Okay, now we have 3 new private keys. So what we want to do, the first thing we want to do is, instead of sending this 0 input transaction to this address, let's send it to a real address. So we're going to make an address, and recall that an address is just the hash of a public key. So we're going to take A. Let's see. Oops. public key. Let me just check if that's the right method on that one. Yep, here's the example. So now we're going to send our money to A's address. Okay, so now we are A. Let me see. So I actually need to turn this into a real address because I need to use it down here. I need to do that yet. I don't need to do it yet, but I'm going to because we're going to have to verify this at some point. Just bear with me a minute. Okay. Address. ABC, ABC. Okay, so now we're sending this to A's address. And now, for this transaction, we're going to pretend that we are A. No, I'm sorry. Yeah, here. So for this guy, we need to supply the public key of the output that we're spending. So this is a single input. We need the public key corresponding to that single input. Now we know that we just did that, and that's the public key for A. So A, public key. Is that how I did it? Did I make bytes out of it? Yes, I did make bytes out of it. That would make sense. Pub text. And like I said, I'm going to reformat it. It's nice when everything lines up. So now we have, I didn't have any multi-input transactions. That's unfortunate. Well, this one's still going to fail. So let's just fix this. 70. And we actually need to change this, right? This needs to be the address of B and the address of C. B address. C address. And then, in the interests of keeping things slightly interesting, we need another key. We could just send it back to A. Let's make a big circle. So that's this transaction, number one. And we're going to spend this output from B and this output from C. So when we do that, we need to have two public keys in here. We need to have, which one did I spend first? I spent the second one first, of course I did. Text, C, public key, and B. And we're going to send it back to A. which would be a address, obviously. A address. I'm sorry, we need to make an output. Make an output, a address, and we're going to send all 100 back. Okay. So let's just check that I have not messed up the syntax. I have not, somewhat remarkably. So now these transactions look a little different, but we still haven't substantially changed anything because we're not verifying anything. So we need to do another verification. So this is where things become hopefully a little bit clearer. Oh, no, we're not doing that yet. What was I thinking? We didn't sign these transactions yet. It's a bit of an oversight. So when we make this transaction, we don't have to sign this transaction because it's a Coinbase transaction. It's giving us free money, essentially. This transaction definitely does need to get signed because this transaction is spending A's money. So we better make sure that A signs it. So like I said before, the first part of verification is making sure that the public key here that we've supplied does indeed match the address of this transaction. So this address has to match this public key. Or rather, this public key has to match this address. And then we have to sign this second transaction with the private key that corresponds to that public key. So let's do it right here. I can move this afterwards, but for the sake of being on the same screen, it's important. Sign TX. So this transaction is going to get an additional member. We may have to use more than one. Signatures equals sign. What are the arguments for sign? A private key and a message. That's all I need. P in private keys. But what is the message? So in Bitcoin, the message is essentially the whole transaction, because it's written in C++, I think, maybe C. So it's all just bytes. Very easy to just say, take this chunk of data, consider it as a string of bytes, and give me the and sign it. Or give me the hash or whatever you want to do. In Python, not quite so low level. So what I'm going to do is I'm going to create a function that takes a transaction and returns a string of bytes that is essentially that transaction. So transaction to bytes. So let's just remind ourselves, and by ourselves I mean me, what a transaction actually consists of. Okay, so I'm not super interested in the transaction ID, since that is a function of the other things. So what I'm going to do is I'm going to return, I don't know why I deleted that. I'm I'm going to return a bytes object that is tx inputs, all of the inputs. Just get rid of that. Now plus tx public keys, yeah, plus the public keys plus outputs. Now the outputs and the inputs are not text, so we have to make them text before we do this. Public keys are already text. So an input is a transaction ID and a number. So this is going to be transaction ID is also a number at this point. It's going to be a string. Let's make the transaction ID into a not yet. So what we're going to do, that is a number, so we want to string it. Input. Let's go up here so I can remember what I'm talking about. I'm going to take the string of the transaction ID. Plus string output. TX inputs, which we already have. Okay. So this is an array of string, which is not exactly what we want. Actually, we don't have to do it this way. We can actually make our lives a little bit simpler. Python will output a nice string, a nice unique string for this that has the data in it, since it's a dictionary. You won't just get a dictionary object. Let me just check that. Strip A. Yeah, so we get a unique representation anyway, but we do need it to be a bytes object, so we're going to encode it. Okay. So now we have all our inputs encoded. Public keys are already encoded, thankfully. I do prefer to have the operators at the end. Now we're going to do the same thing for the outputs. Strip out dot encode for out in outputs. So what we should end up with is an array of bytes objects, which we then join together here, and that'll be the string representation of our transaction. Let's just do this just to see what it looks like. BC0. Oops. Okay. So we have a bytes object that has no inputs. Yep, that's accurate. It has an address and an amount. This looks like it's just giving me the outputs. What's up with that? Oh, the other two are empty. Yeah, okay. Yeah, it's still unique. So since we're not actually verifying it, let's just check. Okay, expected a bytes load object and found a string. Okay, well, this should be a dictionary anyway. Ah, nope, that's wrong. Oh, right, okay. It's this guy. That should be the bytes-like object. Yes, okay. Good. Ah, here we go. Here's our input and our public key, so-called. Great. Done. Bye-bye. And bye to you. So, now we have, after all that, a little bit more effort than probably I was expecting. We have a way to turn a transaction into a unique string. And since we can turn a transaction into a unique string, we can then sign it and be assured that the uniqueness, be assured that the next time when we come to verify it, we'll just run the transaction through this exact same transformation, and we'll verify it, and it should come out being correct. Okay, so now our message is tx bytes of the transaction. Okay, so now we see sign transaction. And we're signing it with A's private key. No, not this one. This one. This one doesn't need a signature because it has no inputs. This one needs a single signature because it has a single input, and that input belongs to A because we sent the money to A in this transaction. And this guy, sorry, here we go. Got to be an array. This guy is transaction number 2, and we have to sign it with C and B. C and B. Okay. Fingers crossed. Ah. Yeah. Well, that'll teach me to change variable names in the middle of writing the code, won't it? True. Fantastic. Okay, so now they're signed. It doesn't do us much good unless we can verify. So now we're back to where we were, where I said we were a few minutes ago. We'll move on to the verification part. And like I said before, the first part of verification is to make sure that the address is correct for the public key. I'm going to call it verify sig. Okay. So we are going to verify this single transaction against the blockchain. We use BC in this anymore. No, I don't really need that. I guess I just added it because that's what I do. Okay, so first, to the public key. I do need the blockchain. So, for in transaction inputs, and we actually want not just the input, we want the public key as well. So I'm going to do zip of tx pub keys. Okay, so we're iterating over the inputs and the public keys at the same time. Let me see. Yeah, okay. I'm going to add one more method for my convenience because I know that I'm going to change it later. Is get tx. Right now it is still just an index. Right, the transaction ID is still just an index, which is fine for now. But I know that's going to change. So I'm introducing this method now so I can just change the method later and not have to worry about where I've actually used it. Okay, so we need the address. We need to get the address of this public key, get the address from this public key, I should say, and verify that it matches the address that is in the input. Okay, so if address pub key equals, and this is where things get slightly complicated. So I need to look up the transaction. Get tx bc input txid. So I've got the transaction that I'm claiming to be able to spend, or part of which I claim to be able to spend, and I need to look at its outputs. And specifically, I need the one that corresponds to my input. Right? Recall that an input is just a, let's have a look at it. An input is a transaction ID and an output number. So here I'm using the transaction ID to get the transaction, looking at that transaction's outputs, and looking at the specific output that corresponds to the input that I claim to be able to spend. And from that output, I want the address. Just made it on the screen. So, if the address of my public key that I've supplied in the transaction matches the address that my corresponding input claims to be able to spend, then I have passed stage 1 of the verification. So if it's not equal to, then we have an invalid transaction. Pub key to address mismatch. There we go. Nice little message, and we're going to return false because it does not match. So that's actually the easy part. No, I guess actually they're both equally pretty easy. So now we verified that the public key matches the address for all of our inputs. And now we have to sign with those public keys to verify that we have indeed got the private key that corresponds to the public key that corresponds to the address that we claim to be able to spend. Okay, so for sig pub key zip tx signatures tx pub keys. What do we want to do? We need to get the message. Thankfully, we have a method for that. Transaction. Transaction to bytes. Yep. And if not, verify. Let's just go back up here. Verify is one of the cryptographic primitives that we created, and its arguments are a public key, a signature, and a message. So pub key, sig, and message. Turning false, and we also want to print invalid tx bad signature. Bad signature, no bitcoins. TX. That's it. So let me just move some of these things around. This guy, and one right after the other verification method. And these two. Should I just move these two? That's fine. These turn one up here. Okay, so here we verified the chain to make sure that the spends are consistent with each other. And here we're going to verify the signatures. Now, so here we're going through all of the transactions. So we can just tack something on the end. Almost on the end here. On the end here. Oh, not there. Here. There we go. If not verify sig, we'll give it the whole blockchain and the specific TX that we're interested in. Turn false. No need to add a message because we already got a message from here. Okay, now let's see if this worked. Let's find out where I made the typos. So I know in our example we have three transactions, one that doesn't need signing and should therefore just pass by virtue of not even going into these loops. Oh, hold on. It's not going to pass. Because no, it's untrue. Okay. Yes. So this one will pass because it doesn't go into either of those two verification loops. This one ought to pass because I signed it. And so should this one. Okay. Not very surprised by that. Key error signatures. I bet it's one of the no. Key error signatures for sig pokey sign transaction. Alright, probably a naming thing. Key error signatures transaction. I don't think I actually got the spelling wrong, but I'll give it a try anyway. Yeah. Alright, let's do some debugging. Actually, there are only 3 of them. How bad can it be? So this is the very first transaction, and okay. So even though it doesn't go into the loop, it's still trying to figure out if it needs to go into the loop. And it can't because there are no signatures. So that means that my MKTX thingy up here needs to, when it's first created, have the signatures added. But they can be empty. Alright. It's a different message. That's progress. Byte subject has no... Oh yeah, okay, fine. Right, what did I do? Down here. This is assumed to be an actual public key, which at this stage it is not. I think this one is as well. Keys equals what is it? txt to pub, p for public key, for p in tx, the pub keys. And then here, and the same thing down here. Okay, so all I'm doing here is just decoding the text that I put in here back into an actual public key object, and then using that object. So let's see what the next error is. Wow. Is my surprise showing? Okay, good. So that's that. We have created and cryptographically signed a consistent set of transactions and verified that they are indeed correct. Yeah, good. And now I verified that if you change one so that it's broken, it will indeed report an invalid signature. So that's nice. What else can I do to mess with this? I can change one of the addresses. Bad address equals C address to character 5 plus a 1. That's a byte subject. Oops. Let's hope it's not actually a 1 at that position. Plus C. Could have just mixed the two together, I suppose. But 6 onwards. And I'm sending this to C, so let's do that address. Okay, there we go. It works. Only mildly shocked myself. I don't know about you guys. So there you have it. Now, I should say, I meant to say this earlier while I was actually doing it, that this signature and verification pipeline that I've created here is a fixed pipeline. There's only one way to sign and verify a transaction. In Bitcoin, the picture is a little bit more complicated because when you create an output in Bitcoin, you don't just create an address and an amount. You also attach a little script. Now, the Bitcoin scripting language, so to say, is very simple, but it does allow a lot more flexibility, obviously, than a fixed pipeline. So, for example, here, there's no concept of multi-sig. If you have a single, you can only create single ownership addresses and single signatures. And indeed, this entire algorithm would fall apart if you had two signatures for one output. Whereas in Bitcoin, obviously you can have multi-sig, and there are various other things that you actually can do that you can't do here. I don't know if that's interesting enough for a video. Give me some feedback. Otherwise, thanks for watching, and the next, that's it for transactions. So the next video is going to be starting to address putting transactions together into blocks. Thanks for watching. Hopefully see you next time.